Hi, I'm Jack Baker. In this presentation we'll discuss a number of results related to directionality of earthquake ground motions. This is work performed by Shrey Shahi here at Stanford as part of his PhD thesis in support of the NGA West 2 ground motion prediction project. The motivation for this work is that while the response spectrum of a single component ground motion is well defined, for a multi-component ground motion there are a number of ways in which one can define a response spectrum, and there have been changes in those definitions over the past few years among various communities, and so relationships between those values is becoming increasingly important. So we're going to discuss a number of results about how those different definitions relate to each other. Traditionally, response spectrum of a multi-component ground motion was computed by taking two orthogonal components of the horizontal ground motion, computing a response spectrum for each of those individual components, and then taking a geometric mean of the two response spectra. That's what ground motion prediction equations typically provided up until about 2008 era ground motion prediction equations. The NGA West 2 project in 2008 moved to a slightly different definition, this SAGM wrote I-50 definition. This was an attempt to produce a definition that's somewhat similar to the geometric mean definition, but was not dependent on the orientations of those two orthogonal components that were selected. It's a bit of a complicated definition, so I'm not going to discuss it in great detail in this presentation. So I'm going to avoid spelling that one out in detail. More recently, taking a median response spectrum or a maximum response spectrum over all possible orientations of a multi-component ground motion have become more popular in the latest NGA West 2 projects, as well as in ASCE 7 has specified an alternate definition. So we're going to talk about those in a little more detail in a moment. And then we'll talk about the engineering implications of using these various definitions as well. So to make sure we're all on the same page, let's talk about response spectra for a single component ground motion, or alternately put, a single orientation. So if I have a ground motion in a given orientation, this is specified by acceleration of the ground. So we'll use the X double dot notation for acceleration, and a subscript G to indicate this is ground acceleration. We then specify an elastic oscillator that has a given mass and stiffness, indicated by M and K. The mass and stiffness define a frequency of vibration of this oscillator under free vibration. We also specify a damping coefficient. This is typically 5% of critical damping for these response spectrum calculations, but can be other values. So under this elastic oscillator with the given mass and stiffness and damping, the acceleration or displacement of the top of that oscillator relative to the base is given by this differential equation. We can solve that numerically with the specified ground acceleration to solve for x, the displacement of the top of the oscillator, as a function of time. So we get out a x as a function of time result from that numerical solution of that differential equation. And our response spectrum is actually a pseudo acceleration spectrum. So what we do is we take the maximum value of that acceleration over time, then we take the maximum value of that displacement over time, then we estimate a maximum acceleration by multiplying that maximum displacement by stiffness over the mass, or the natural frequency vibrations squared. So that's a pseudo response spectrum. The non-pseudo version of the response spectrum would be to take the maximum of x double dot of t over time, but that's typically not what we are doing, even though we call these response spectra. Okay, for a directional dependent response spectrum, we can think this over. So in the x direction, I still have the same ground motion, and this figure here on the left is kind of a cartoon of a plan view of horizontal ground shaking at some location. So in the x direction, I'm going to have my same acceleration of the ground as a function of time. In the y direction, I'm going to have shaking of the ground as a function of time in this other direction. And at some arbitrary angle away from x or y, I can also compute a ground motion by just simple trigonometry, that if I know the acceleration in the x direction and the acceleration in the y direction, I can take sines and cosines of those to find acceleration at some arbitrary orientation. Okay, if I take Okay, sorry for the delay. I had a little problem with the pen here. Okay, if I take that ground motion in this z direction, which is some angle theta away from the x direction, I can now put that z as a function of time into my differential equation. So this is the same differential equation we were looking at on the previous slide, but now with z double dot as a function of time of the ground input on the right hand side, and I could solve for the response of some oscillator in that direction and compute a response spectrum in that direction. I guess I should also say that this calculation is going to provide a pseudo-spectral acceleration at a single period. I can just repeat this calculation for a number of periods of vibration of this structure by changing k and m and compute a full spectrum here. Okay, so the thing I can notice is that because this is a linear differential equation up at the top, I can decompose this left-hand side, or I can decompose the right-hand side into a x component contribution of the ground shaking and a y component contribution of the ground shaking. Those are each going to produce a component of the oscillator response in the z direction, and I can kind of decompose that using the definitions on the previous page, and I'll see that the displacement of the oscillator in the z direction as a function of time can be easily computed as just the displacement of an oscillator in the x direction times the cosine plus the displacement of an oscillator in the y direction times the sine. And then if I were to take my definition of spectral acceleration from the previous slide, that my spectral acceleration in the z direction is going to be the maximum value of z of t over time, I can put in the right hand side of my above equality, and I will see that I can find a spectral acceleration in some arbitrary orientation theta if I know the response of an oscillator in just the x and y direction. So that makes it quite easy to find these response spectra in any orientation. I don't have to redo any oscillator responses at arbitrary orientations if I just solve for those oscillator responses at two orthogonal orientations, the x and y in this case. Okay, so now if I've got oscillator responses and spectral accelerations at arbitrary orientations, I can now think about ways to compute response spectra that incorporate kind of variations in direction. So here to illustrate, I have this polar plot on the right-hand side, which is the response of a 1-second oscillator to an example ground motion. So this is a ground motion from the Morgan Hill earthquake in 1984, just to illustrate. So the solid line here is a displacement of that oscillator in a three-dimensional space. So this is kind of an easy way to summarize those x and y oscillator responses from the previous slide. But those displacements are normalized by the maximum displacement that the oscillator saw over time, just to give us units between 0 and 1 in this figure. So we see that we reached a maximum oscillator response in this orientation that's kind of 260 degrees away from this 0 reference angle. And we see that in that plane, kind of the 260 degree to 80 degree plane, we get very large responses. In a perpendicular orientation, we get small responses, meaning that an oscillator that's oriented at, say, 160 degrees is not going to see a very large response. We take the maximum over time of the different components contributions of oscillator responses here to find a spectral acceleration, and shown in dashed lines is spectral accelerations of a 1-second oscillator as a function of theta, this angle away from 0 degrees. So we see that in the 260 degree direction we have a spectral acceleration that's very large, and in the opposite 180 degree different direction we also have that same value. We take maximums of absolute values of responses. And then as we move to some other angle, our oscillator responses are going to be smaller because we're not going to see that full oscillator demand that we saw in this 80 degree to 260 degree angle. Okay, so now moving back to the spectral acceleration definitions that we were discussing on the second slide of this presentation, I have a number of ways in which I can summarize this 2D oscillator response in terms of spectral accelerations. So I could define an x component direction and a y component direction, take the spectral accelerations in those two directions, square them, add them together, take a square root, and that would give me a geometric mean would not quite give me a geometric mean calculation, actually. I would want to take, sorry, we'll do a correction on the fly. I would take the spectral acceleration in the x direction for a given period times the spectral acceleration in the y direction for a given period, and I would take the square root of those two. That would be a geometric mean. Okay, so that's one way to kind of incorporate the multi-direction responses here, but that's going to be dependent on which x and y I choose. So if I choose an x in the 0-degree direction and a y in the 90-degree direction, I will get an answer in terms of the geometric mean response of this oscillator. If I choose x to be in, say, a 45-degree direction and y to be in a 135-degree direction, I could use that same definition, but I would get a slightly different answer for the geometric mean value. That was the original concern about the use of this geometric mean spectrum, and in part the motivation for introducing alternate definitions of response spectra. Okay, another definition I can use, this often is called the maximum direction response spectrum, but a little more formally it's been called the ROT-D100 response spectrum. So the idea here is that for a given period, so the 1 second period is the case over on the right, I can take the maximum value of spectral acceleration that I see over all orientations, and that's going to be my spectral acceleration value. So in this case, it would be that spectral acceleration that was observed at the 260-degree angle. So the maximum spectral acceleration you see in any orientation. Similarly, I could, rather than take a maximum direction value, I could take a median over all possible angles. So I could take these 360 angles. If I wanted to do 1-degree increments, I would get 360 spectral acceleration values. Rather than taking the largest of them, I could take the median of them. And this maybe you can guess from the notation, but the idea is that this 50 and the 100 in the subscript here are indicating the percentile value of the spectral acceleration that one is interested in here. Something to note, if I clear off a little bit of this ink on this slide, is that in this case, where this ground motion is strongly polarized, my median ground motion, I can label it here, or my median spectral acceleration over all orientations is going to be something halfway between this spectral acceleration at the maximum direction orientation and some orientation that's kind of approximately perpendicular to that orientation. If I go halfway over, and if I assume that in a limiting case, that perpendicular orientation has no contribution in terms of oscillator responses, then my oscillator response in this orientation 45 degrees away would be my maximum direction spectral acceleration divided by the square root of 2, because this is a right triangle and so I've got kind of a sine 45-degree term here to convert myself from the long leg of the triangle to one of the adjacent legs. So in such a case, as noted here, the ROT-D100, or maximum direction spectral acceleration, divided by the median direction spectral acceleration, or the ROT-D50 spectral acceleration, that ratio is going to be a square root of 2. That's an upper bound value for that ratio. Okay, and then as I noted on the first slide, there's also this GM ROT-I50 definition. Rather than give you the definition, I'll just give you a little bit of background. So the idea was that with these ROT-D100 and ROT-D50 response spectra, so these are kind of unambiguously defined for a given oscillator period. But if I take this same ground motion, say this 1984 Morgan Hill Gilroy number 6 array recording, if I switch to a 2-second oscillator period instead of a 1-second oscillator period, the orientations at which I see my maximum direction spectral acceleration and the orientations at which I see my ROT-D50 spectral acceleration, those orientations will change relative to this 1-second case. So there's no unique direction at which a ground motion always has its maximum direction response spectrum, or where it has a ROT-D50 response spectrum. So the GM ROT-I50 definition was an attempt to find a single orientation at which the ground motion response spectrum was similar to something like a median response spectrum over a range of periods. So the motivation was to have that single unique orientation. However, the computation of this thing is rather cumbersome and a little difficult to explain, so it's since fallen out of favor. I think the intended advantages didn't end up outweighing the disadvantages. And newer ground motion models are tending to work with this SA ROT-D50 definition. Okay, so an important note here from an engineering perspective is that I've listed here 4 different candidate definitions of a spectral acceleration for this ground motion. For this single ground motion at this single 1 second period, I will get 4 different numbers for those 4 different definitions. That does not mean that the ground motion is any weaker or stronger as viewed via one of those definitions. It's just a different way to describe the same ground motion, and that's important that to think about. Just because I measure this ground motion using a ROT-D50 spectrum instead of a ROT-D100 spectrum, it doesn't mean that I'm assuming the ground motion to be any less intense. I'm just measuring it via a different definition. And we'll talk about that a little bit later. Okay, so some results to discuss now with those definitions in our minds is we can talk about ratios of values of those different spectral acceleration definitions. We can talk about the orientations at which we observe them, and we can talk about kind of the interactions between the orientations of these spectral values and the periods that we're interested in. So let's move into that a little bit. So first we'll talk about ratios of spectral acceleration values. The right figure here is the figure we were looking at just a moment ago. So this is again a 1 second oscillator response shown in a plan view. So if we were looking down over the top of a oscillator that could shake in any direction, we see that it's shaking primarily in the up and down direction when it's exposed to this Morgan Hill-Gilroy array number 6 ground motion. And in a case like this, the maximum direction response spectrum is significantly larger than the ROT-D50 spectral acceleration, as we just talked about with this kind of right triangle type thing. And in such a case, we end up with ROT-D100 over ROT-D50 values that are about equal to the square root of 2. At the other extreme of how this oscillator could respond, here's on the left side, same thing, a plan view plot of a oscillator responding to a multi-component ground motion with horizontal shaking. This is from one of the Chi-Chi aftershocks, and the station name is given here in the lower left. So in this case, the oscillator shook in a number of different directions, and as you move around over the whole range of possible orientations here, the oscillator responses, the peak oscillator responses, were very similar over a wide range of orientations. So I can see kind of maybe a max direction oscillator response here at about the 300 degree angle. I see it also at the 225 degree angle. I saw a very similar response, and using this dashed line here that's going around, this is the spectral acceleration at a range of orientations as computed using the definitions of a few slides ago. In a case like this, the maximum direction, or the ROT-D100 spectral acceleration, is almost identical to the ROT-D50 spectral acceleration. The ROT-D50 spectral acceleration is slightly smaller, but essentially is the same. So in this case, that ratio of those two definitions is approximately equal to 1. So the left case is a lower bound where this ratio is about equal to 1. The right case is an upper bound where this ratio is approximately equal to 1.41 square root of 2. So that's the range of ratios that these two spectral definitions can have. Okay, so now let's think about predicting maximum direction response spectrum. So if we think about the specific ground motion's maximum direction, or ROT-D100 response spectrum, I could also compute that ROT-D100's response spectrum as saying, well, I'm going to compute the ROT-D50 response spectrum, and then I'll just multiply it by the ratio of its ROT-D100 to ROT-D50 response spectrum. So the left and right side are equal in that case. I'll take logarithms of both sides so that I'm working in log spectra. That will be more consistent with ground motion prediction models. That's the second line here. And then I can realize that I have a lot of ground motion prediction equations available. So these are the things like the NGA West ground motion prediction equations that many of the listeners should be familiar with. And the NGA West 2 ground motion prediction equations are going to predict log ROT-D50 response spectra. Okay? And so what they do is they say, okay, well, I can predict your ground motion for a given situation using some function of magnitude and distance, site conditions, rupture mechanism, basins, and whatnot. And I'll have some error terms representing kind of variability in those response spectra that I wasn't able to predict with this ground motion prediction equation. We can very quickly build a ground motion prediction equation for a max direction response spectrum. This is, for example, what the ASCE 7 guidelines would need when they produce ground motion hazard maps for maximum direction response spectrum. So if I desire to have a ground motion prediction equation for this maximum direction response spectra, I can get there by taking advantage of this equality here, and I'll just build in a maximum direction factor that will handle this left term on the right hand side of the equality. And so this model here will have to say that the log of the ρd100 to ρd50 response spectrum is some function. It turns out to can be very well modeled by a very simple function, even a constant, plus some error terms there. Okay? So the idea would be that you can have maybe just a constant prediction as a function of period for this ratio with some error terms. We'll see in a moment that the constant model works fairly well. The error terms are relatively small compared to the error terms on the right hand side. And further, this ratio here is independent of the primary ground motion prediction equation. So it's relatively a simple manner to build this max direction factor, pair it with a much more sophisticated ground motion prediction equation for ρd50 spectra, and very quickly get a ground motion prediction equation for ρd100 response spectra. Okay, so let me tell you a little bit about how Shrey and I worked on building some maximum direction factors, and I'll show you some comparisons to previous similar studies. Okay, so this work was done using the new NGA West 2 database, which is a greatly expanded version of the NGA West database, which is widely known and has been around for about 5 years. There are on the order of 8,000 or 9,000 ground motions in that database initially in its current version. We used subsets of that database that were chosen by the ground motion prediction equation modelers. So there's exclusions for inappropriate data based on the conditions in which it was recorded, or the record processing, or whether it was an aftershock, or things like that. There's a lot of documentation about how that's done in literature produced by the ground motion prediction equation modelers. So we took advantage of their work and reused their data sets to be consistent with those models and to benefit from their expertise. The figure on the right here is a plot. The x-axis is the period at which we're interested in. The y-axis is the number of ground motions that were utilized by each modeler. This is as of November 2011. It's changed slightly since then, but this was the iteration of the data that we used. So you can see, depending on the modeler, there's somewhere between 1,500 and 3,000 ground motions that were used by each modeler. And as you move to the right, to periods of greater than about a second or two, the number of data points or number of usable records starts falling off. That's because some of the recording instruments weren't able to record a high enough quality signal at those long periods to be considered usable after the filtering is performed and considering the signal to noise ratios and things like that. Okay, for each one of those ground motions and at each one of those periods, spectral acceleration values were computed by Shrey. These were 5% damped response spectra at 21 different periods and at all unique orientations in 1 degree increments. I should note at this point, it turns out you only need to compute from 0 to 180 degrees, since the 180 to 360 degrees increments are just the oscillator responses are just the negative of some corresponding increment in the first set. So we have to do 180 unique orientations. And then to start to look at the data, here are some plots. So this is histograms of the data set chosen by the Abramson and Silva modeling team. On the left side here is a histogram of ρd100 to ρd50 ratios. You see they vary between 1 and 1.41, as we discussed a few slides ago. And this is the histogram of ratios observed for 0.2 second elastic oscillators. So for 0.2 second elastic oscillators, many ground motions have ratios on the order of 1.1. We see this high peak here, but we see ratios that range from 1 to 1.4. The right figure is the same calculation, but repeated for 1 second oscillators. So those are oscillators like the ones that were shown in the earlier slides. And you see the ratios shift slightly, and the larger ratios, closer to 1.4, get relatively more frequent compared to the 0.2 second case. So we could say that these longer period ground motions are slightly more polarized in terms of the oscillator responses. Okay, so we have all of these data points, several thousand data points. For each one of these histograms, we can take a geometric mean of those ratios. That's what's plotted on the y-axis of this new figure. The x-axis is showing the oscillator period at which we're interested. So for the 0.2 second oscillator period, that's the left histogram, the geometric mean ratio is just a little bit larger than 1.2. So our geometric mean is somewhere in here. For the 1 second oscillator period, the geometric mean is slightly increased, something more like 1.25, so maybe somewhere in here. Okay, that's the 1.25 value plotted at the period of 1 second. That's repeated for 21 different periods, and we see this trend of slightly increasing geometric mean ratios with period. So lows of about 1.2 and highs of about 1.3. Okay, so that was using ROT D100 to ROT D50 spectral ratios. There's all of these other definitions floating around as well, so let's take a look at what we can see. So here's a plot of a number of different ratios versus period, just like the previous figure. The dashed red line here is the same ratios that we were just looking at in the previous slide, running from about 1.2 to 1.3. Down at the very bottom of the figure are a couple of previous results. So when ground motion prediction equations switched from geometric mean spectral accelerations to GM ROT I50 spectral accelerations, there was in some cases a need to first study how different those ratios were, but also potentially convert between them. That's we see down in this bottom solid line here. The ratios between those two are on the order of 1.01 to 1.02, so just a percent or two different between those two ratios. And those ratios can be used in the same way as the ROT D100 ratios that we were discussing earlier to build an updated ground motion prediction equation. So that change in definition doesn't make too much difference. Then, as the ground motion prediction equations evolved from GM ROT I50 to ROT D50, there was a need to evaluate the difference between those two. So here that's shown in the dashed dot line down at the bottom, and we see that at longer periods, heading towards 10 seconds, that difference can be up to 5% difference, so that starts to become perhaps consequential. And then we can piece these models together as well. So in the solid black line, we could say if we were interested in a GM ROT I50 to ROT D100 ratio, we could get there by taking a ROT D50 to ROT D100 ratio and a GM ROT I50 to ROT D50 ratio. The product of those two would get us up to the solid black line. So that's taking two results off the plot and putting them together to get that solid black line. I should note there are a number of other authors who have proposed ratios of these types as well. I'm just taking some examples here to illustrate these. In large part, the various authors are very consistent in these ratios that they report, as detailed in with more numerical results in the forthcoming peer report that'll document the same information. Just to illustrate the consistency between these various models, so here's a plot of 5 different authors who have studied ROT D50 divided by GM ROT I50 response spectral ratios, geometric mean. I should be a little more precise. So the 4 authors at the bottom of this list all studied ROT D100 to GM ROT I50 ratios. The solid black line, the Shahi and Baker report, which is the one that I'm discussing results from today, that was actually a ROT D100 divided by ROT D50 ratios model, but it was pieced together with the ROT D50 to GM ROT I50 ratios model of Bohr 2010 to make a fair comparison here. So the thing to take away here is that these models are all in quite have relatively strong consistency. They don't vary by more than a few percent at any given period. Some of the difference is due to some authors choosing to fit some parametric function, while other authors provided just raw data. Some of the similarity comes from substantial overlap in the data sets that were used for this calibration. But even in some other data sets, these ratios seem to be relatively consistent. The one thing that is changing here that should be quite clear from this figure is that these ratios certainly are a function of period. So the short period oscillators are much less polarized than the long period oscillators, as seen by the increase in the y-axis values moving from left to right in this figure. One other thing to note is that as these maximum direction spectral accelerations were adopted in hazard maps in the building code community, in ASCE 7 specifically, and in the NEHRP provisions that are related to that, spectral acceleration ratios were provided there that are indicated by this NEHRP 2009 line. Those are significantly different than the other published models. In part, that's due to I think an inappropriate processing of the ground motions with respect to some equations we looked at a little bit earlier. When we think about putting together this amplification factor in the ground motion prediction equation to get a or a Rote D100 response spectrum, this is not exactly the mathematics that was thought of by the NEHRP provisions. The authors who put together the table of max direction factors, I think it was just an error in the way that it was thought about there, and could easily be corrected in future treatment of maximum direction factors. So something notable is that those NEHRP 2009 factors are not consistent with all of the published work on this topic. Okay, so this is a variation of these ratios with period. There's also a great deal of interest in does a ground motion's Rote D100 to Rote D50 spectral ratio, does it vary with other properties of the ground motion? So are near fault ground motions different than far field ground motions? Or are large magnitude ground motions different than small magnitude ground motions? Are soft site condition ground motions different than stiff site condition ground motions? And the answer is generally not really. So here is a plot of the y-axis value is this Rote D100 to Rote D50 ratio. The left figure is for 0.2 second oscillators, and each point on this figure is one individual ground motion. So these ratios were computed for each of several thousand ground motions, as discussed earlier, and here now they are plotted against closest distance to a fault rupture, or RRUP in the GMPE language. So you can see a couple of things in this plot. So the overall geometric mean Rote D100 to Rote D50 ratio is indicated here in the horizontal dashed black line. If one is to do a regression analysis and try to build a regression function that predicts predicts this Rote D100 to Rote D50 ratio as a function of distance, you'll get this solid red line. The slope on that red line is not significantly different than the horizontal black line here, indicating there's not a strong dependence on distance. The entire process is repeated over on the right side for the 1 second oscillator period. We see the same thing. So there's a slight increase in these Rote D100 to Rote D50 ratios in close, but it's really not a strong effect. And the differences here were, in the 1 second case, we're talking about a 1.24 versus a 1.25 ratio here. So it's on the order of a 1% increase in the Rote D100 ratio relative to if you ignored this effect. The same plot has been produced for a number of other variables as detailed in a forthcoming peer report, making plots of these spectral ratios versus magnitude versus directivity parameters versus a number of other parameters of potential interest. All of them actually have less strong effects than this case. This is the strongest case of any predictor parameter, and it's not very strong. Just to show you the potential impact here, so in black is shown the overall geometric mean Rote D100 over Rote D50 ratio that I have shown a few slides earlier. In the dashed red line is shown a distance-dependent prediction. So we provide an alternate model where you can make a Rote D100 to Rote D50 ratio prediction as a function of distance. The functional form is shown here. So it's the log ratio is linearly varying with distance. That's the regression form that was shown on the previous slide. And we provide the A0 and A1 constants in the peer report. If one is to do that and then make a prediction at 0 kilometers, so right at the fault, you would get the dashed red line in this figure. So you'll have increases on the order of 1% or a little bit more in the Rote D100 to Rote D50 ratios. This is consistent with previous research on this topic. Jenny Watson-Lamprey and Dave Bohr specifically had some language a few years ago when they were studying these types of ratios and said there's a small effect from distance, just like we see here, but for most practical purposes that they could imagine, they indicated that it would likely not have any engineering impact. And we agree with that sentiment here on the basis of this further analysis. Okay, another thing to consider, so we've been looking at this ratio. So A is some constant here, and it's a constant for the log Rote D100 to Rote D50 ratio, so it'll be somewhere between the log of 1.2 and the log of 1.35 or something like that, based on those previous slides. There's also variability in these ratios, as we saw a if I back up a couple slides, we can see that just because the average ratio of rho d100 to rho d50 is 1.2 for a 0.2 second oscillator, there's clearly some scatter here, that some ground motions have ratios up to 1.41 and some have ratios down to 0. So we want to think about that scatter, and that's done in these ground motion prediction equations via event-to-event residuals and within-event residuals. So we do this mixed effects regression to separate out residuals caused by it's kind of common to all recordings in a given event versus residuals that are related seemingly independent from one recording to another, even within an event. Just to show you some typical numbers here. So the event terms in this regression are on the order of 0.01 for this study, and the within event standard deviations have, or within event residuals have standard deviations on the order of 0.08. If we compare those to the primary ground motion prediction equation, so here I'll use the Campbell-Bezorgnia 2008 NGA prediction equation. So they provide standard deviations. This is all for 1 second spectral acceleration values. So they provide standard deviations of 0.255 and 0.568 for these two terms on their term. Okay, so if I was to put these two values together in this top equation here, I have 4 contributors to uncertainty, the within event and between event residuals on each of these two terms. So in the Campbell-Bezorgnia model, I put these two standard deviations together, and they lead me to having a standard deviation overall for this rho d50 prediction. In their case, it's actually a GM rho I50 prediction, but quite similar numerically. So they start out with a standard deviation of 0.623. If we were to roll in the extra uncertainty from this rho d100 to rho d50 ratio, we end up with a total standard deviation on the rho d100 model of 0.629. So we're in the third significant figure before we see any changes in these standard deviations. So the implication here is that the standard deviation of the rho d100 predictions is essentially identical to the standard deviation of the rho d50 predictions. Introducing this maximum direction factor does not increase the standard deviations of these ground motions, or ground motion prediction equations. And to me, that's intuitive in that residuals relative to ground motion prediction equations for, say, rho d50 values are quite often off by 100%. Or not often, but it's not too surprising. This standard deviation is saying your average error is on the order of 60% of the value of your prediction or something like that. So when we add on this ratio that's only varying in a relatively narrow range between 1 and 1.4, it doesn't add any great deal of additional prediction uncertainty. So in the forthcoming NGA2 peer report, we will provide these standard deviations so we'll provide these numbers for the 1 second period as well as comparable numbers for all other periods. But for all practical purposes, these standard deviations can be ignored, and it's a quite good approximation to just take the standard deviation of the base ground motion prediction equation and just treat that as essentially equal to the standard deviation for the rho d100 ground motion prediction. Okay, we've talked about ratios for a little bit. Let's talk about orientations of these max direction values. So there's been thought and a number of studies looking at, are these spectral accelerations preferentially oriented such that the maximum direction response spectra can be predicted ahead of time if you knew the geometry of the fault that produced that ground motion. So here the way that we'll do this is we'll say let's take a fault that's rupturing along a length. So this is say a plan view of a strike slip fault, and we see the rupture dimension, and we've got an angle at which that fault ruptured. We can call that the strike, and then we've got some site nearby that fault where we record a ground motion, and we know the orientation of the strike of that rupture that produced the ground motion. We can then move at some arbitrary angle away from that strike parallel orientation, and we'll move around until we find the orientation of the rho d100 response spectrum at a given period. And we're interested in, are those orientations completely random relative to the strike, or do they have some preferential orientation? The speculation is generally that the fault normal orientation may have a larger probability of seeing this high amplitude response spectra due to polarization of the ground motion from radiation patterns and from directivity effects. So just to show you some some example results before we look into the statistics. So these two figures on the right are, again, plan view of oscillator responses. This is a 1979 Imperial Valley recording. This is a near-fault recording that saw directivity effects. And rather than plot this purely polar, we have plotted on the x-axis direction. This is the strike parallel displacement of the oscillator, and in the y-axis direction is the strike normal displacement of the oscillator. So the lower figure shows the response of a shows the response of a 3-second oscillator, and the maximum response of that oscillator is largely in the strike normal direction, which is what might be anticipated for a site that experienced directivity effects. But if we move to a 1.5 second oscillator in the top figure, that oscillator, the largest responses are primarily in the fault or in the strike parallel direction, so in a quite different direction. So we want to look at kind of over a big statistical sample, how are these orientations lined up relative to strike normal and strike parallel. We're also interested in, as I change periods here, so say from 1.5 seconds to 3 seconds, even in the same ground motion, how much do these orientations change? That has important engineering implications. As I'm thinking about the demands in my building in a single orientation, say on a single frame of my structure, should I be thinking about whether Rho D100 spectral accelerations could be observed at a number of periods in that single orientation, or will the orientations vary such that that single frame may not see Rho D100 spectral values at all periods? Okay, so this key parameter is this alpha parameter right now, and keep in mind this picture here. Alpha equals 0 indicates that the orientation of Rho D100 was in the strike parallel direction. Alpha equals 90 indicates that the Rho D100 spectral acceleration was in the strike normal orientation. So here are plots of a bunch of histograms. So each one of these histograms runs from alpha equals 0 up to alpha equals 90. And then the heights of these bars indicate kind of what fraction of the ground motions had an alpha value at that particular orientation. Okay, so these are histograms. These are binned over periods. So we've already, for a given ground motion, we can compute alpha values at 21 periods, and those are all grouped into here. We'll pull those back apart in just a second. Then the grouping out into this pattern here is looking at different ranges of magnitudes down the y direction. So the top row here is magnitudes between 5 and 6. The second row is between 6 and 6.5, 6.5 to 7, and then 7 to 8. So splitting up the ground motions in the database according to the associated earthquake magnitude. Along the x direction is the distance away from the rupture. So 0 to 3, 3 to 5 kilometers, and so on. So up in this top bin, this would be all ground motions that were observed from earthquakes of magnitude 5 to 6 between 0 and 3 kilometers from that fault. There was actually no ground motions in that bin, but in all the other bins there were some ground motions to look at. And so let's take an example, say, of the magnitude 6.5 to 7 bin at a distance of 30 to 40 kilometers. So in here we have these heights indicating how many observations we had of alpha values at a given orientation. Given the statistical precision here of the limited data set, this is essentially uniform heights of those bars across all alpha orientations. So this indicates there's no preferential orientation of alphas among magnitude 6.5 to 7 earthquakes at distances of 30 to 40 kilometers. That's not always the case. If I take that 6.5 to 7 bin and I move into less than 3 kilometers, I see some sort of strong preference towards alpha values of 90. So that's the fault normal orientation. So if I'm in close to moderate to large earthquakes, we see this in kind of all of the magnitude ranges. I have a preference for seeing my Rho D100 value in the strike normal orientation. That's what kind of intuition suggests, and we're interested in statistically how clear of a signal is that. So the 0 to 3 kilometers case, it's quite clear that there's that preferential orientation. The 3 to 5 kilometers case, there's also a pretty strong preferential orientation here. But by 5 to 10 kilometers, it seems to have mostly disappeared. So there's some hints in a couple bins, but in other bins they look quite uniform, or even kind of going backwards, suggesting we shouldn't squint too hard at these given the finite amount of data we have. So it appears that within 5 kilometers there is this preferential orientation. Okay, the magnitudes don't seem to matter too much here. So if we look from top to bottom in these rows, they all look rather similar. So we can, to help push our data a little further, we can merge all those magnitude bins. And so here's a plot of kind of all magnitudes merged together, and all distances between 0 and 5 kilometers merged together. So we took the left two columns out of the previous slide, put them into a single bin, but then split things out with varying period. So now we have the same, the x-axis is the same, alpha values between 0 and 90, but each one of these subfigures is for a specific oscillator period. So down to 0.01 second oscillator periods, up to 10-second oscillator periods. So we're looking at short periods versus long periods. Is there some preferential orientation of these max direction spectra? And you have to squint a little bit at these. There's a kind of limited data, but after staring at it a lot of different directions, with these two figures as well as a number of other figures, it seems that there's a little bit of a split here, that for the 0.5 second and longer oscillators, there is this preferential orientation to strike normal, whereas for the less than 5 second oscillators, those histograms look essentially flat. There doesn't seem to be any apparent polarization of those oscillator responses. That again is relatively consistent with intuition that if it's directivity effects causing these polarizations, that should be strongest at kind of half-second and longer periods for earthquakes of this magnitude. Okay, another way to look at this is to look at ratios of response spectra in the strike normal direction or the fault normal direction. So we pre-specify that orientation, and then we compute a response spectra for each ground motion, and then we compute the Rote D50 response spectra for each of those same ground motions and take those ratios. And these lines here are averages over all ground motions in a given distance bin. And the distance bins are given down here in the legend. So this is our rep values between 0 and 5 kilometers, 5 to 10, 10 to 20, 20 to 30. So if there was no preferential orientation of the Rote D100 spectra, or no polarization of these responses towards the fault normal direction, we would expect to see ratios of these values that are equal to 1. And indeed, that's basically what we see for all of the bins of ground motions that are more than 5 kilometers away from the fault. As we move in closer than 5 kilometers from the fault, we see this average line coming up about 10% larger than the Rote D50 spectral accelerations. It's indicating that the fault normal ground motions do tend to be stronger than the average direction, or the Rote D50 ground motions. And this is happening for kind of 0.2 seconds and longer, or something like that periods, which is consistent with the previous slide. At those short periods, even in the in-close, there's no clear trend that the fault normal ground motions are larger than kind of any other direction. Okay, so to summarize some of the previous slides' results, there does seem to be some dependence on distance and period of this orientation of the Rote D100 spectra. This is consistent with previous work, previous observations. So as you move in with distances less than 5 kilometers, this is rupture distances, and as you move to oscillator periods greater than a half second, there seems to be some preferential outcomes of the Rote D100 response spectra occurring in a fault normal or strike normal orientation approximately. So we saw that preferential orientation. That's not the same thing as saying that the Rote D100 response spectrum always occurs in the strike normal direction. So there's a preference towards that, but it's not the case that this is always what happens, as we saw in those histograms. It's just a skewing of the histogram, but not a 100% grouping of those histograms in strike normal orientations. All right. If you move outside of 5 kilometers or you move to short periods, the distribution of these orientations appears to be apparently uniform. We looked at splitting that data out by magnitude and saw no differences between the small magnitude and large magnitude data. Similar studies were done with respect to directivity parameters and some other parameters, and there was no other parameter that seemed to help provide any indication of preferential orientations. Okay, so that's the orientations of these response spectra at a given period. The other questions we might ask is that if I move to 2 different periods, so coming back to our figure from earlier, if I look at a 1.5 second period and a 3 second period for this ground motion, how much difference are those azimuths or those alpha values at different periods? And we can ask some related questions about these directions here. So let me show you a few results of that type. So here, what we did is we took results similar to what was shown on the previous slide. We found, so let's take this upper left figure. So we picked a first period of a 1-second oscillator, and then a second period of a 2-second oscillator. For each ground motion in the database, we computed the orientation of the Rho D100 spectrum at 1 second, the orientation of the Rho D100 spectrum at 2 seconds, and we took the difference between those two. So that difference is going to range between 0 degrees, indicating that the two directions are perfectly parallel with each other, and 90 degrees, indicating that those two directions are orthogonal to each other. Then for all of the ground motions in the database, we built this histogram to see how often did we observe various differences in orientations. So we see that you're more likely to have parallel orientations than perpendicular orientations, as indicated by this decreasing histogram moving from left to right. And this is generally the case, but it varies a bit depending on which periods you're interested in. So we have 1 second versus 2 seconds up top, 1 second versus 5 seconds in the lower left. So there's a bigger difference in the periods, and we see that distribution flatten out about a bit more. Same thing is done on the right for shorter period pairs, and we see similar trends. So in general, what happens is that the further apart the two periods of interest are, the more likely the orientations are to be significantly different from each other. And there's some tendency to head towards similar orientations, but it's certainly not always the case that these orientations stay in the same direction. We could move over to the upper right figure. So this is 0.1 second oscillators and 0.2 second oscillators, and so that's a relatively small period spacing, but there's still a something on the order of a 1 in 3 or a 1 in 4 chance that the difference in the orientations could be greater than 50 degrees. Looking at this histogram here, so it's even in small changes in period, you can see big changes in the orientation of these Rho D100 spectra. So it's certainly not the case that there's a unique orientation of a multi-component ground motion at which the Rho D100 spectral values will be observed at all periods. Okay. Another way to look at this is to fix the oscillator period. So here, this plot on the left, we've got 3 different oscillator periods, 0.1 seconds, 1 second, and 10 seconds. Then we will choose the initial angle of the Rho D100 orientation. So let's say in the example case that we've looked at a bit through this presentation, if we choose this orientation of the Rho D100 response, and then I want to move in directions away from that Rho D100 response, so if I move to some other orientation here, I'm going to compute some angle phi relative to the Rho D100 angle. So that's the phi, the x-axis on this left plot. And so I know that spectral acceleration is going to decrease as I move away from the Rho D100 orientation, and this plot is indicating how much I'm decreasing on average. So this is the geometric mean value of the spectral acceleration at my new orientation relative to my my Rho D50 value. Okay, so if I'm at a phi of 0, I'm at my Rho D100 orientation. So I'm going to see amplifications of 1.2 to 1.3. That's exactly those amplifications, the Rho D100 to Rho D50 values. So this is SA Rho D100 over SA Rho D50. All right, so the denominator is Rho D50. The numerator is SA at the orientation of Rho D100. Okay. If I move about 45 degrees away, I'll get back to ratios on the order of 1 because I'm looking at approximately my Rho D50 orientation. So my numerator and my denominator are approximately equal. There's a little bit of nonlinearity here regarding the geometry and the way that these things interact. So we're back to approximately the Rho D50 spectral acceleration values, and if we move more than 45 degrees away, heading towards orthogonal from Rho D100, will actually be less than the Rho D50 spectral accelerations on average. So that's another type of result. It's and the quantitative results of this type are provided in the peer report that's forthcoming. Okay, one example of just thinking about these different ways in which we can define ground motions. So here is a response spectra for just a single ground motion. So this is a recording from the magnitude 7.6 Chi-Chi earthquake. It is a near fault site, so it's 3 kilometers away from the rupture. And we can define, so again, this is one ground motion. It has a unique strength of shaking, but we can define several different response spectra here for it. So in the bluish color here, I could define a ρd50 response spectra. That's what your standard ground motion prediction equation is going to produce, the NGA West 2 generation at least. The NGA West generation would produce that GM ρd50 spectra, which is similar but not identical to this. We could also produce, in red here shown, the ρd100 response spectra. That's going to be larger than the ρd50 response spectra by definition. And we could predict what that would look like using these ρd100 to ρd50 ratios discussed earlier. Here it's just computed for the specific ground motion. And these are, again, 1 to 1.4 times bigger than the ρd50 spectra. The thing to note with both the ρd50 spectra and the ρd100 spectra is there's no single orientation of this ground motion that has that response spectrum. This is different orientations at each period that produce those numerical values. If I want a single orientation of a ground motion, I can look at it in a couple different ways. So here in this first dashed line, I can look in the fault normal direction for this earthquake, take that component of the ground motion, and compute its response spectra. So it's plotted here in this green color, and you can see that in some periods, so in this kind of 2 to 3 second period, that response spectrum is a bit larger than the ρd50 ground motion, but it's not as large as the ρd100 ground motion, so there aren't very many directions in which the fault normal orientation was as large as ρd100. Actually, over at about 0.02 seconds, there's one period in which that happened, but in a lot of cases, the fault normal ground motion is weaker than ρd100, and in some cases, it's weaker than the ρd50, so at say a 1 second period or so, it's actually quite weak in the fault normal direction. Okay, so that may not be necessarily the spectrum that I would want to use for some engineering analyses either. Another way I could do this is I could say I'm going to pick a period of 1 second. I'm going to pick the orientation at which the 1 second oscillator has its ρd100 response spectrum. So kind of saying if I'm most interested in 1 second, let me choose that direction where I'm going to see the ρd100 value. And then for all other periods, I'm going to keep the direction fixed. So I'm going to use that single orientation as defined by picking the 1 second oscillator. And for that single orientation, I'll compute the response spectra at all other periods. So for a range of periods around 1 second, this oscillator in that direction has about the ρd100 response spectrum. As I move away in periods to kind of significantly more different periods, that orientation is not necessarily the ρd100 orientation. And there's likely not a single ground motion that's been recorded where there's a single orientation that we have the ρd100 response spectrum at all periods. So these dashed lines are, there's a single orientation associated with those response spectra, either the fault normal orientation or this specific orientation for the 1 second max direction. The solid lines are there's not a single orientation at which we ever see that response spectra. So there's kind of pros and cons to both ways of defining a response spectrum for a given ground motion. So to conclude some of these results, just summarize a few things. So there's going to be kind of a number of popular spectral acceleration definitions floating around in the engineering seismology and the engineering community for the foreseeable future. And given the multiple definitions, we have a need to convert between predictions for one definition versus a intended application that uses another definition. But as we saw towards the beginning of the presentation, there's a number of models available for those different conversions, including the new ρd50 spectral accelerations that will be adopted by newer models such as NGA West 2 and forthcoming NGA East models and others. We presented some results here of ρd100 to ρd50 spectral acceleration ratios. Those are consistent with previous studies, but they're tailored specifically to this new ρd50 definition, so they're intended to be kind of used in that way, but no new surprising results here relative to previous studies of this type. We do see a dependence of those ratios on period. There's a weak dependence on distance, as we discussed. Could likely be ignored for all engineering purposes that I can think of, but if for some reason one wanted to include it, there is a quantification of that. There's no obvious dependence on magnitude or directivity related parameters, as could be determined from the data set considered here. And finally, the standard deviations of these ratios are quite small relative to the standard deviations for ρd50 spectral predictions, so it's not necessary to update standard deviations when you're doing a conversion to a max direction or a rho D100 spectral prediction, although we will provide those standard deviations for anybody who would be interested in having them. Okay. And one note is that because the standard deviations are small here and there's not a dependence on magnitude or distance or anything like that, it can be shown that that means it's possible to compute a hazard curve for SA rho D50 and then after the fact multiply that hazard curve by your rho D100 to rho D50 ratio and get a hazard curve for SA rho D100. That's only because of this very simple relationship here, and that can be shown with a little bit more effort, though I didn't discuss it today. Okay, finally, I just want to give a few thanks. So first of all to Shrey Shahi, who produced all of the results that were shown here and has developed all the written documentation of these models. The sponsor of this work was the Pacific Earthquake Engineering Research Center via the NGA West 2 project that provided the financial resources and all of the data that made this study possible. And there was a project review team as well of all of the people listed here that provided kind of oversight of this work and a number of useful comments and a lot of helpful feedback as these models were being developed. So their input is greatly appreciated. With that, we'll wrap up this presentation. Hopefully that's been a useful overview of directionality of ground motions and some of the implications of thinking about direction-dependent response spectra and how one can work with them in a kind of quantitative way from the perspective of hazard analysis, and a little bit of thought given to the engineering implications of this work.